All right, this is a mock live coding interview for a Microsoft technical slash phone screen for a software engineering internship role. We're going to go ahead and cut straight to it, but it is going to be it's around 30 to 45-minute leak code style problem that you'll have to walk through while you explain and solve it. Okay, we'll jump straight to the chase. Um, this problem is called add two numbers. It is a leak code style problem. So you can check out that link from LeetCode. And there's two non-empty linked lists that represent two non-negative integers. And the digits are stored in reverse order, and each node contains one digit. The goal is to add two numbers and return the sum as a linked list in the same reverse order format. So each linked list node is represented by a list node object. They define you the list node class here, which is good. So in the first example, we can see that we have 243 and 564. Those are the reverse versions of the number. So that would just be 342 and 465. Adding those give you 807, which is just 708 in the reversed order. So you would represent the linked list of nodes in the reverse order. In the second example, we have a 0 and a 0. So adding those up will just simply be a 0. And in the third example, we have our first linked list and our second linked list. And adding those up would give us 89990001. And this makes sense because if we were to reverse the numbers and then do the addition, that would give us that result. And then we end up flipping the numbers again as a linked list to solve it. Cool. So first things first, the best way to get started is to first figure out the input and the output. We know that our input is going to be two linked lists, L1 and L2. And our output is another linked list that is the reverse sum of L1 and L2. Not too difficult. So it's really nice that it's in reverse order because then you don't even have to worry about reversing the linked list and all of that, because if you're already anyway have to return it in reverse order, you're basically just adding the numbers. It's kind of the same concept basically. So if I do 243 and 564, I get the same kind of thing where I guess you can say 7 and then 10 and then that'll give me 8. So it's kind of the same thing. We can just handle the nodes and then we can store a separate variable as the carry. Okay then, so I guess we can start this problem. We're gonna call this as problem 1, and this takes in two linked lists, and it's expected to, like I said, return us a linked list. That is the reverse sum of both the linked lists. Cool. So to get started, the first thing that we need to do is we need to first create some kind of dummy node. The reason why this dummy node is important is because we need a way to add elements into our linked list. If we started with a head, then we would have to deal with the special case situation with just the head itself where we had no more elements in the linked list. It would just be a little bit weird. So by having a regular dummy node and then having a linked list branch off of that, it makes concatenating into a linked list a lot more easier. So we're going to call it a dummy node, and we're going to call it just a list node of 0, just to make sure, just to have some node to start off the problem. And this is the list node module that has been given. From here, the next thing that we need to do is we need to store a temporary variable that starts at our dummy head. Well, it's not really our head, but it's our dummy that branches off into the head. The reason why is because we need some way to traverse through our list our newly concatenated linked list, right? As we add elements into it, we need a way to traverse through it. So we're gonna call this temp, and we're gonna call it, we're gonna make it equal to dummy, because we can't traverse the dummy node itself, because then we need to be able to return the full linked list at the end that stores all the references to the other nodes. So we need to be able to keep dummy, and we need to be able to return its next node, which is the head of our newly concatenated linked list. So we need to have a way to traverse through that as we concatenate nodes. So we're going to create a variable called temp in order to be able to do that. The next thing that we need to do is we need to take care of a situation where we have a carry. Obviously, if you have a thing like 4 plus 6, we're going to have 10, and we need to be able to carry. The value that comes from it. So if we have like 4 plus 7, we have 11. We need to carry that 1. So we need a variable that stores the carry and moves it forward to get our new total for the next node in the linked list. So it's a way to carry it over into the next iteration of a loop through the linked list. So we need another variable that tracks that carry. Next things next, we need a way to loop through our linked list so we do the repeated addition process. So in order to be able to do that, we need two variables. I'm going to call them cur L1 and cur L2. That way they track the current node in each linked list that we can traverse through. So we'll call this L2, and then we'll set the first one to L1. Cool. And then we need to be able to do a while loop that traverses through the linked list until there's no more elements present. In order to do that, we can just say while cur L1 or cur L2 or carry. What this tells us is that as long as we have elements in the first linked list, as long as we have elements in the second linked list, and as long as we have a carry, we can go through the while loop and add the elements in the linked list. So the way we start this problem is we need to be able to get each digit in the linked list, right? So we're going to call this digit 1, and this is going to be the the current node in the first linked list, L1. In order to be able to do that, we need to be able to first check if we have a current list node, and if we do, we need to be able to get its value, because that's what's going to give us our digit. So in order to be able to do that, we're going to say cur L1.val, but we can only do that if we have a current L1, or if we have a current node in our L1 linked list. Otherwise, we're going to say this is going to be 0, because if we have a situation where it's like 342 plus 56, there is a hidden 0, so you can basically do 354 plus 056, or 342 plus 056. You can have like a 0 placeholder to do the addition from. So that's where that 0 comes from. So if we don't have a node, we can just treat it as a 0, because adding anything to 0 does nothing. That same kind of idea comes into the second digit as well, where we get the current node in the linked list and we get its value, but we can only do that if the current node in the second linked list exists. Otherwise, we can just set it to 0, and adding anything to 0 does nothing, so we can just set it to 0 if there's no node. The next thing that we need to do is we need to create our node that represents the total. Our total node is going to be equal to digit 1 plus digit 2 plus our carry, right? Because if I carry over a 1, I need to add that with my digit 1 and digit 2, and then I'm going to have that result as total. From there, all we need to do is we need to have a variable that stores the result of total, and then if there's a chance that there's a carry, we need to update that in our carry variable as well. So in order to be able to do that, we can have a result, and we can have result equal total, and we can have that as total %10. The reason why this works is because if we have something like 5 plus 6 is 11, we know that we have the 1 as our result, and then we just carry the other 1 over. So doing %10 gives us that last value, which is what we need as our answer. When we do regular addition, that's what happens, right? We get that last result, and then we have to carry over the additional 1 that is there. And speaking of that additional carry, doing total integer division by 10 will give us that first value, right? If I do, let's say for example, I did 12 divided by 10, that's just going to give me 1. That's going to give me that first most value. Same situation if I do 112 and I do integer division by 10, that's going to give me 11. Yeah, it's going to give me 11. So that's going to be every digit up to the last. So in this situation where we have 11, we're going to get that 1 from the beginning, and we're going to add that into our carry. And then from there, all we just have to do is we have to concatenate this result into our new linked list. So all we'll just say is we'll say temp.next is equal to our result, and then we're going to say temp is equal to temp.next, because that's what's going to go and traverse through the nodes in our newly concatenated linked list. This is a problem though, because this is a linked list of list nodes, not just a linked list of integers. So we need to wrap it around a list node. And then from there, all we just have to do is, now we've concatenated this result into the linked list, we're going to traverse our temporary pointer that goes through our concatenated linked list, and then we need to go through the nodes in our L1 and L2 linked list of our inputs. So in order to be able to do that, we have to first check if we have them. If we do, we'll just say cur L1 equals cur L1.next. Similarly, if we have cur L2, we'll just move that node over as well. And then from there, we're pretty much done. We can just return dummy.next, because like I said in the originally, dummy.next is our head. So dummy is just a way to be able to easily concatenate a new linked list. So dummy.next will be the start of our linked list as head. So the next thing that we need to do is we need to be able to test. Let's go ahead and test what we wrote. In the first example, we got our digit. First digit's 2, then second digit's 5. We add those because they both exist. That gives us 7. Our carry is 0, so our total is 7. Our result is going to be 10, and we don't have any carry. That's just 0. And then we're going to add that as a list of 7. I'm going to write down my result here. And then we do have a current node. We move that forward. We do have another. We have a current node of the other list. We move that forward. So now we have 4 and 6. Those both exist. So then we can add 4 and 6. We get 10 plus our carry, which is 0. So now our carry is set to 1 and our result is set to 0. So that's going to be 0 into our linked list, which is what this code does right here. Then we check that node does exist, so we move both our pointers forward. Then now we have 3 and 4. Those both exist, so we add them into 7, but we have a carry of 1. So we add that into 8, and then we add that into the end of our linked list. And then since both of those don't exist, so we don't move the node forward. And then we no longer have a current L1 and L2, so we are basically done with our code. And that is our resulting linked list. So for the second example, kind of the same idea. We go through 0 and 0. We just add them. That just gives us 0, and then we return that. This isn't really anything weird. We just go through the process one time in the loop, and then we're done. In the third example, we start with the first 2 digits. That becomes 8. We carry over a 1 because 18, we carry over a 1. And then we have 9 plus 9, that's 18, but we have a 1 to carry over. So that's a 19. That gives us a 9. We carry over another 1. That process, we can repeat that 2 times. Then we have 9, and then we have nothing, right? Because at that point, when we get to this part of our linked list, L2 doesn't have any more nodes, but we can set that to 0 because it's just adding to nothing. 9 plus 0 is 9. We have a 1 of a carry, which is 10. We repeat that 3 times, and then we add our carry finally to the end of our linked list as a 1. Okay then, so it looks like our test cases pass. When it comes to the time and space complexity of this problem, the time complexity of this problem depends on whichever linked list is bigger. So if L1 is bigger, and we're going to say M is the size of L1 and N is the size of L2, then that means that if L1 is bigger, then that means that's going to be the time complexity. So we can really say it's the O of max of M and N, where M is the length of L1, and N is equal to the length of L2. And then our space complexity is O of 1, because we're not storing any additional auxiliary space. Okay, and that's that.